Hello, we're Group 5. Today we'll be showing you our EQ project. We consist of Dylan Shapiro, Alyssa Cutney, and me. I'm Joe Hammer. Here's our general overview. Today we'll tell you a little about EQ the way we created a recursive descent parser, as well as the way we created a BNF grammars, which we wrote in C, C++, and Python. We took an original EQ project and embedded C and C++ recursive descent programming libraries into the Python EQ project, and then we compiled it by using CMake. So what is EQ EQ has an overall objective to create a handwritten math expression solver which takes an image of an expression and outputs the answer to the problem. Here are some steps taken to complete it. First, we produce our own dataset by taking pictures of numbers 0 through 9 and mathematical symbols, and then we label the symbols within the images, and use object detection model architectures from TensorFlow's Model Zoo that have been designed for the Common Objects in Context dataset, also known as COCO. Then we use a semi-supervised dataset that generation technique to expand our training data. And finally, we present our solver by creating a program that uses our algorithmic and model pipeline. The objective is to create a handwritten math expression solver which takes an image of an expression and outputs the answers to the problem. The model outputs labeled bounding boxes such as classes, boxes, and scores, and an alignment algorithm using bounding box coordinates and providing predictions. We ordered the predicted symbols into an equation. We then use Python's eval function to solve the equation. How did we improve EQ As explained in the previous slide, the model's output is run through an alignment algorithm to create an equation. This alignment algorithm, model, and the user are not perfect, so to help with user experience, I would like to propose a solution to remove possible false positive and false negative situations. For example, our camera is taking a bad quality picture, therefore the model predicts badly, or the alignment algorithm hits unhandled edge cases where there is no check before trying to solve it using the Python eval function. This recursive descent parser allows us to identify that the equation is valid before trying to solve it using the Python eval function.
So next, we're going to talk about the recursive descent parser. So you're wondering, what is a recursive descent parser? A recursive descent parser is a top-down parser because it builds a parse tree from the top down and then from left to right. The actual tree is not constructed, but is implicit in a sequence of function calls. It's in the same way the actual tree is implicit sequence of reductions used for a shift-reduce parser. This type of parser was very popular for real compilers in the past, but it's really not as popular now. But a recursive descent parser is often written entirely by hand and does not require any sophisticated tools. It's a simple and effective technique, but it's not as powerful as some of the shift-reduce parsers, not the one presented in class, but fancier similar ones called LR parsers. Here is a diagram of a recursive descent parse tree, and here you can see in the diagram all of the different states in here. So you see the terminal states, the non-terminal states, and you can see going through each parse tree that there's a given string, and for each given string, you'll see the non-terminal states recursively calling the next non-terminal state until it reaches a terminal state and returns. What is a BNF grammar? So it stands for Backus-Naur form. It is a formal mathematical way to specify context-free grammars. It is precise and unambiguous. And before BNF, people specified programming languages ambiguously. For example, with English. So how RD Parser improves EQ solve? So with the BNF grammar, we are able to produce a recursive descent parser. This recursive descent parser will allow us to validate the string equation is valid to solve before attempting to actually solve it. This allows us to let the user know if it was a blurry photo or it was a non-solvable equation. And then a stretch goal for this would be to use the BNF grammar to eventually identify if the equation is solved or needs to be solved. The requirements. So we have some functional requirements. So functional requirements include that the recursive descent parser shall use an alignment algorithm to create an equation in the output. It also shall make use of the RDP library implementation. The parser will use bounding box coordinates and then provide predictions to then order the predicted symbols and the numbers into an equation. The parser will allow a user to identify the handwritten equation is actually valid before it tries to solve it. And also the parser will be using Python's eval function to actually solve the equation that is presented once validated. Environmental requirements are that it shall contain a C or C++ compiler. The environment shall have any needed Python libraries or packages installed. And lastly, the source code shall be built with CMake, which is seamlessly being integrated within the existing EQSolve project. Lastly, we have some other requirements. So these shall keep the current graphical user interface that EQSolve already had. The parser's graphical user interface shall contain the following. There shall be a title that'll say original image with the image of the handwritten expression that's at the top of the application. Underneath that, there's going to be a thing titled boxed image with the image below it with the handwritten expression that has each symbol that is boxed. And then underneath that will show the actual expression that the parser validated and found with its detecting.
So our design was as follows. The high-level design looks like this. There's our RDL component with BNF grammars. Each grammar consists of a toolbox configuration, and a parser. This is an overall architecture design. The Flash application has EQSolve, which has a math library, recursive descent parser, alignment tool, and a machine learning model. The actor interacts with the Flash application, of course. Challenges we faced and how we overcame them. Setting up the work environment was challenging. Writing a Python C extension with Swig was challenging. Building with CMake was a little hard to configure, and however, we ended up overcoming that challenge, and it's seamlessly integrated with the project. The recursive descent parser library implementation was written in C and C++, also in Python. Creating the BNF grammar was a tough challenge. Creating the recursive descent string parser was also challenging. Setting up the work environment consisted of installing the C++ compiler, installing needed Python packages, some being OpenCV, Flask, NumPy, TensorFlow, object detection utilities, and installing CMake. Writing a Python C extension, we needed to install and configure Swig. The C extension tool allows us to use our C and C++ RDP library within the Python web application. Swig is a software development tool that connects programs written in C and C++ with a variety of high-level programming languages. Swig is a free software, and the code that Swig generates is compatible with both commercial and non-commercial projects. Actually, TensorFlow is a program that utilizes Swig. A little fun fact. And this is an example of the Swig Python C extension. You have to create this interface file and run this Swig command. These are some of our sources. And now I will demo the code.
Cool.
Okay, so I'll demo the program. Let me just. As you can see, this is the start screen. It's not pretty, but gets the job done. There's a choose, so we could choose a file. This opens up. You're able to pick an image, and then when you press the upload button, it redirects you to the next page where our results should show up. As you can see, the original image is posted, and also the boxed image with its predictions and the percentage the model predicted, and the equation is also there with the answer. So you have the option to try another. If you press the try another, you get redirected to the first page, and you're able to pick another equation and upload it. As you could see, the same is shown. However, this time the model predicted poorly. As you can see, it thought the division symbol was a 1, and the 2 was 2 parentheses. I'm not sure why. And our recursive descent parser was able to identify that before even trying to solve it. And then we let the user know that this is an invalid equation that could not be solved. And that is it. Thank you.